All right, so I'll be earlier today, Quincy kind of mentioned cloud object stores and the cloud optimized HDF5 files. So I'll be talking about cloud optimized HDF5 files. And it's more of an update and continuation because I talked about them, I think, the last year's HUG. So I cannot go back and for people who are new to this concept to sort of talk at length. I have to kind of go further, but I'll try to give enough context, hopefully, that those find it useful and understand the main points. So long story short, for big intro, about 2016, the NASA Earth Observing System Data Information System, which is in charge of managing the NASA's collection of Earth observations, mostly from satellites, but other platforms, airplane, and some ground, decided strategically to move all their data and all their operations into cloud, anticipating a huge volume and increase in data and simply realizing that no on-prem solutions will be able to be to achieve the goal of really offering public the maximum access to this data. So talking about what Quincy said 10 years later. Sorry?
Keep the best new slides because we still see your first slide.
Yeah, this?
Okay, thanks.
Yeah. So that's the, so what, long story short, they have a vast collection of HDF5 files. Some of them are called NetCDF4. And so this when they decided to move into cloud and they started putting these files into cloud object storage, and specifically they chose Amazon Web Services, and therefore cloud object stores were S3. Those files provided a significant technical challenge with a very, very poor performance in data access. And second, the HDF5 library really was not sort of ready to provide cloud native access to those files and data. So cloud optimized HDF5 files is the attempt to sort of offer first order solution and help to NASA what can be done to improve data access for their HDF5 files and make HDF5 still a viable choice for their missions to store data in. So what is cloud optimized HDF5? Really, it's the old HDF5 file format, just the layout of bytes in those files is different. And that's a good news and bad news. The good news is it's available already now, even in some later, older versions of the HDF5 library, which is significant because a lot of these NASA places are very slow to upgrade their HDF5 library. The bad news is that it's only valid to the newly created HDF5 files. And so the millions of HDF5 files that NASA currently holds are really not cloud optimized. So how that's going to play out is to be seen. But at least there's a light at the end of the tunnel called cloud optimized HDF5 files. So the two most important things in this cloud optimized HDF5 files is first that the chunks are becoming bigger. And the reason for them I'll explain a little bit later. But the next one is that the internal file metadata is now laid out in contiguous blocks. And so getting what's in the file is becoming a much more efficient operation now. So all these two things lead eventually to the most significant important thing in cloud optimized access, which is reducing the overall number of S3 requests. And once you achieve that, then you can see some definite direct improvements in performance. And again, I talked a lot about this at the HUG event last year, but I also include this QR code to my video of that same talk at the conference that happened 2 weeks before that my HUG talk last year. And so you can go and see in detail where it explained these different methods, how one can optimize cloud, their HDF5 file. So I'm not going to go and repeat that. So what is, again, after that meeting, so I'm talking about the last 12 months, I had a lot of interactions with some users and producers of data in the NASA ecosystem. And so what follows is kind of this lessons learned, if you will, or at least current advice of what worked and how things panned out when they try to create HDF cloud optimized HDF5 file. The one thing when I'm talking about is I want to be clear: chunk shape, chunk size. When I say chunk size, I mean in bytes. Chunk shape is the number of elements per each dimension, which is also important parameter of a chunk. But I'm focusing on chunk size here mostly. And that chunk size is prior to any compression or any other filtering of these chunks. So essentially just sort of the number of data array elements times the data type size of in bytes of the one element. So that's basically what they're talking about. The NASA satellite data overall doesn't really have cases already that have largest chunks, and there is a historic reason for that. And well, most likely of them is that still the library comes with a dataset chunk cache of 1 MB, and that's by default. And people for a long time, even now, especially these NASA users, they really don't know that they can change that. And so a lot of chunks were going into several kilobytes and that kind of stuff. However, for this exploration, even H5 repec was not really the right tool to use because, again, NASA files tend to have hundreds to thousands of HDF5 datasets in them, and it's not really easy to apply H5 repec and get sort of a version of this file with much bigger chunks. So that's kind of a little impact in that regard, that I don't have a lot of experience how the big chunks really impact everything else. That's still kind of now maybe happening or is going to happen, but not so far. However, what we do know is that larger chunks definitely will make them being less in a file per data set. And that all leads reducing the internal file metadata again. So that's something that we already know is going to happen. So consolidation of internal metadata, as I said, there are 3 different methods I laid out last year when I talked about it, but the one that really got tested is the one that's called, as you can see here, paged aggregation file space management strategy. And I like to use the term paged file. It's easier to pronounce. Basically, the file is divided in file pages. Some file pages hold only internal file metadata. Other file pages exclusively hold the data. And that file page can be set at file creation. And that's as far as I know, and the people I worked with, that's the only approach they used. And I'll explain later why that's really important. So here is where that really benefits. Right now, HDF5 library is not, as I mentioned, really not a first-rate citizen in cloud-native computing. And therefore, these pages, when the files are paged, enables library to read data in pages, which means that besides getting the chunk that really is needed, the library will get the page in which this chunk is. And that, again, if you're lucky and the chunks of the same data set are in the same page, you get more chunks than you really asked for, which may help later. And so, again, overall, this yields that the number of SRE requests may go down. And so right now, the page files are the best case for HDF5 library as far as data access. Some other methods that do not use HDF5 library, they cannot, as far as I know, they still have not adopted this paged approach. So they still go after chunks. And that's why making chunks bigger actually helps those other methods. On top of pages and reading data in pages by the library then also has this page buffer cache. So it not only brings more chunks than it's needed, those chunks can be cached in this buffer. So again, if you're lucky and if your use case depends on coming back for the similar data or for the chunks that happen to be in the same page, then this cache can also help prevent excessive number of SRE requests. Again, getting better performance. The downside of this page file is that the files compared to the original tend to be bigger. How bigger depends, again, how these chunks are compressed. In other words, every page, when it's filled, it leaves some free space. And in some cases, with these people that I worked with, the increase was beyond the threshold they were really willing to accept, because for them, these files are getting bigger, therefore their cost in paying for storage in S3 are going higher. And again, these are missions that have terabytes and terabytes of data, so it's not like small increase. However, so far we were able to find the way how these files are created and generated to keep the increase reasonable, sometimes quite small. So far they decided to accept Cloud Optimized HDF5 files for their next versions. Chunks, as I talked a lot about them, I'm not going to spend too much time here, but basically what we really need to now think about is two things. First of all, how big the chunks should be per file, and the other thing also what compression method to use for these chunks. NASA data almost exclusively uses zlib compression, and that's driven primarily by the need of interoperability. NASA data can be accessed on all kinds of computers, in all kinds of stages, with all kinds of older, newer, latest software. It's really the most diverse computing environments that you can think of. And so zlib is the most common denominator that everyone thinks will be available. And therefore, they're using zlib. But however, the question now becomes, is the zlib really that good compression method? Because if we are able to compress these chunks better, then more of them will fit into a file page, then more of them may go into less amount of file page. So kind of all these things is connected with each other. And so that's where we are right now. Don't have anyone who's using anything other than zlib. That's another story with availability and ease of use and installation of HDF5 compression filters. But I have not seen anyone really going for something other than zlib. So what was done generally is that people tried and played with different page sizes. Rechunking, making bigger chunks is now just happening maybe the last 2 months. One satellite mission is now exploring making bigger chunks in their files, so that's still to see how that's going to go. So they use 4, 8, and 16 megabyte page sizes. And when they tested some access and performance, 8 megabytes was kind of giving the best performance. Not terribly obviously best, but noticeable best. For those files that were tested, most of them had all their internal metadata in a single page, which is the best possibility. And so one thing that was discovered, as I already mentioned, depending how people create these files, if you are creating files in steps that include several times of creating file, then open the file, add some data, then close the file, then open the file, add some data, then close the file, with these page files tend to balloon in size. And so I was able to give them some advice that they could manage this increase in file sizes. But it's just an indicator that once you kind of change significantly something, how these files are created, all kinds of issues start popping up left and right. Here I want to give some results. So what happens to chunks when you page that file? I examined one file from one specific NASA instrument. That one is on the International Space Station, and it's essentially a LiDAR that shoots 6 laser beams down. This is an interesting case because there's a lot of data sets in this file. I mean, if as you can see, there's a 4,100 plus compressed data sets in this file, single file. And I said, all right, let's see what happens with those chunks when the file is paged. Chunks were not touched; they were original one. In other words, H5 repec was used only to sort of just create a paged version of the file. And again, there's a lot of these results, but some interesting things when you start looking into this file that, 27.5% of these chunk data sets have chunk sizes less than 10 bytes, which is, ridiculous. First, why create a chunk data set in the first place? However, this file has everything. And so they have almost 4.5% data sets that have chunks bigger than the file page. In other words, these chunks are bigger than 10 megabytes. So one chunk is bigger than a file page. And again, if we went to a higher page, these files will grow in size too much. And so this is an interesting case, definitely. Number of stored dataset chunks, as you can see, there's a lot of them that have only one chunk, and the number is exactly the number of datasets that have chunk sizes of less than 10 bytes. So you know what this means. It means there was a single element, probably float 32 or float 64 or something, and that was like that's already chunked dataset. But there are no, for example, dataset with more than 100 chunks. And this is an interesting statistics. For example, how many datasets are spread in how many file pages? And the vast majority, 85%, turned out to be in the single file page. Now, not all of them were in the same file page, but they were in a single file page, which means that the library would then read just that one file page and have all the chunks for this dataset already obtained. However, what are these datasets? Are they really the important ones in the file, or they're just there for some auxiliary data? That's another story. So I do think that these chunk datasets they are spread through more file pages are really the important ones, the ones that people would go for the data really. So other things also here, but here is an interesting thing that people are interested, that I work with, like how much should my chunk cache size be to have all my chunks in a single, in the cache. And again, good news is that 95% of datasets are good with 16 megabyte chunk cache. But again, I think these 192 that are needing more than 16 megabytes are probably the ones that are carrying the most interesting data in the file. So that's that. The library improvements is what, someone tell me how much time I have left. What Dana mentioned yesterday when he talked about the state of HDF. I'll just mention here again, we're making incremental and meaningful improvements, but they are spread over time. So we're kind of catching up to what the HDF5 library really could be and should be at this stage of cloud computing. Only the 1.14 version is getting these updates. So whoever is using anything older, that's not going to be, they're not going to get any benefit of that. And so what's been done here? Someone mentioned yesterday, for example, the need of so many settings in HDF5 library and that they need to set them by themselves. That's exactly the feedback I'm getting from these NASA users and producers that I'm working with. In this particular case, for example, it's a page buffer cache size. The library was so finicky before that if you didn't tell the library the page buffer cache size and the file was paged, the library would throw an error, so you couldn't use it. So imagine in a very diverse computing environment, when you don't know ahead of the time, is this HDF5 file cloud optimized or not? That's a big headache for people who just want to work and analyze data. So that's changed now. Now the library is much more forgiving. You can say that set the page buffer cache size. You still have to do it because the default is 0. But at least now, if the file is traditional file, the library is not going to create an error. If the file tends to be paged, the library will work with page buffer. So that's easing up a lot of workflows for NASA users. We fixed a couple of bugs that were discovered during this work, and there is a lot of these new things that may come. I'm hopeful still for the 114 releases, but as I said, the rate at which this happens is not really doesn't match the urgency of the need. And so, talking about ZAR, I think that this is where people, when they need to make decisions which way to go, that's where basically they're looking at. The ZAR world is already ready for a lot of these workflows for which HDF library is not. And that's pretty much what I wanted to talk about. I have some benchmark data, but I don't know if there is enough time or not to show quickly. I can see if there are any questions.
Okay, so there is a comment that LC4, right? LC4 was this standard works much better than anything else, so this is one thing. But the problem is that NASA don't want to try anything else, CV, because it's available. And my question was, have you tried in your own benchmarks to use compact storage for those small data sets and use page file?
You mentioned something about compact storage?
Yes.
Am I right? So compact storage is not recommended by NASA for NASA data producers because these alternative methods who are not using HDF5 library, they cannot use compact data set. And because, again, as I said, the NASA sees ZAR world as the primary consumer of these files. They are now, if you are a compact data set, they need to extract the data and store it in some JSON outside of the file for the ZAR world to be able to use it. And so that's right now the recommendation is to avoid compact data sets.
Okay, thank you.